Thanks. I'll begin with a word of prayer. Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. I just pray you help us to use this time wisely, Lord, to glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. So I figured it'd be good today to go over the quiz from yesterday, right? Hopefully the internet will work in here so I can actually get my scan. Find out soon. While I'm doing that, is there anything else you guys need to have any questions about from homework in particular?
Yeah.
Yeah? Okay.
From 10.7, I didn't see the answers were in the file.
Sure.
10.7. So I was just curious about how they got 10.
10.7, number 10.
Yeah.
We can definitely do that. .7, number 10. Oh, fine. I guess I'll hold it. So I'm supposed to find, is it the arc length?
Yeah.
So find the arc length of graph y equals f of x for x an element of the closed interval from 1 to 4. And here we have f of x equal to 1/8 x squared, right, minus the natural log of x. All right, so I've been trying to convince you guys that the parametric viewpoint is the most general one and the most useful one. So with that in mind, what is the parametric version of this curve? I mean, it's kind of a silly one. We put x equals to t, right? And we put y equals to 1/8 t squared minus the natural log of t. If you'd rather, you could just put x equal to x and y equal to 1/8 x squared minus natural log of x. It's kind of all the same. I'm just doing t to sort of connect with our larger story in here. So dx dt is what? dy dt is what? So we get dx dt is 1, dy dt is 1/4 t minus 1 over t, right? Do you guys agree? So we want to find the speed. What's the speed? So the speed, of course, is ds dt, but you know, I use the symbol v for the magnitude of the velocity, the speed. So that's the square root of dx dt squared plus dy dt squared, which is what? Looks like we got 1 plus this thing. Right? All right, so therefore, the arc length will be equal to the integral from 1 to 4 of basically just v dt, right? But v dt here is the square root of 1 plus, and I'm going to FOIL this stuff out if you don't mind. That's 1/16 t squared minus 2 times 1/4 t times 1 over t, right? Plus 1 over t squared. Would you guys rather I use x? I mean, I can use x. It doesn't make a difference to me. Notice anything nice about this? Like the t's cancel, right? You notice what happens here? This here is actually just minus what? Yeah, it's minus 1/2, isn't it? Yeah. And then that over here, and the minus 1/2 and the half go together to give us the integral from 1 to 4 of the square root of, well, 1/16 t squared minus 1/2 plus 1 over, or excuse me, plus 1/2 plus 1 over t squared dt. It would probably have been helpful if I just left it multiplied like it was before, so you could kind of see what's going on, right? Like, it's almost the same algebra we just did. What is this? This is 1/4 t, right? Plus 1 over t, right? Quantity squared. If there's any step that most people would get stuck on, it should be that one I just did. Right? That takes some insight to see that that's actually the square of something. Right? But it is. My computer in the way? Okay, so once we have that, then I think everybody knows what to do, right? So that's just 1/4 t plus 1 over t dt, which we get 1/8 t squared evaluated from 1 to 4 plus the natural log of t evaluated from 1 to 4, which is going to give me 1/8 of 16 minus 1 plus the natural log of 4 minus the natural log of 1, which is 0, so who cares? And so this is 15 over 8 plus the natural log of 4, I think would be the answer there. Does that make sense? So were you stuck on the algebra part, or?
Yeah, I didn't see
But you was a setup, right, though? Like you had the right setup, but with x's maybe, I mean, x's is fine. I just keep hearkening back to thinking of it parametrically, because for me, the idea that we take the parameterized curve and find the speed is almost a universal principle. You use the speed to construct so many different things, right? So we use it to calculate centroids, we use it to calculate surface area, and we use it to calculate arc length, of course. All of these things are based on finding the speed and doing some kind of associated integral, right? Would you guys be more excited if I told you you could have a 3 by 5 inch card for the next test? Okay, that has nothing to do with course evaluations. It is something that just comes to you from the, no. So, but yes, I think that would be appropriate for this test, because there's a lot of different formulas floating around that might help you out. Don't get used to it though. I can't do that for the final. Oh, I know. But it's true. Okay, so, because if I do that for the final, then I have to ask you harder problems. And I'd rather ask you easier problems and not have a note card, right? Because if you don't have a note card and I ask you integrate sine squared, that's actually something, right? If you've been paying your dues in here and doing the work, when I say integrate sine squared, you should be like, oh, I can do that. That's a problem on the final? Yay. Now, if you haven't been following along, The integral of sine squared is this mysterious thing I keep doing and you're not understanding, you know? So, oh, was the other questions about homework? You can ask more questions about the homework if you have more. Is that just that one? What do you think about it? We'll come back after the quiz. Let me find my laser. Here we go. So we're supposed to calculate the arc length, centroid, and area of the surface of revolution formed by the curve described by r equal to 5 for 0 less than theta less than pi over 4. So this is kind of a boring curve. It's just like a little bit of a little arc of a circle, right? And it's annoying because it's not very symmetrical, right? I can't argue the centroid of x or the centroid of y is equal to 0, right? I mean, I do think it's probably obvious that the centroid is along the line theta equals to pi over 8, you know? So I guess if you were going to try to game the system and do something algebraic, that would be my starting point. But I should probably include some sort of wording like use calculus in my test to keep you from doing that, because that's not my intention.
Which is figuring out arc length. It's just the radius of the circle.
Well, that's not the centroid, though. The centroid's off the arc.
I know, I was just saying for arc length.
Oh, yeah.
Does that matter?
Oh, yeah, you know, this, yeah, if you didn't do this I am not so unreasonable as to say that you had to do this calculus here. I'm just doing it to illustrate a general principle, yeah. Which is that there's a calculation that has to be done to calculate arc length usually. Admittedly, though, both most of you and myself could have just written down 5 pi over 4 without thinking there. So, now the centroid is, by definition, 1 over the arc length, integrate x times the speed d theta, 1 over L, integrate the y times the speed d theta. In this case, theta is the parameter, playing the role time did. And so you do the calculation. You got 4 over 5 pi, 5 cosine theta, 5 d theta. That gives me one pair of the 5s cancels, left with a 20 over pi. Cosine integrates to sine. So I got sine pi over 4 minus sine of 0, which gives me 10 root 2 over pi. And the other one, I integrate sine, I get minus cosine, and I end up with 20 over pi, 1 minus root 2 over 2. So there's my centroid, this guy, comma that guy, and it kind of makes sense because it's right about where I thought it should be geometrically. Check the numbers. You guys get this? Okay, somebody did. And then the surface area, well, it's not much harder, right? I have to integrate 2 pi y times ds, but ds is v d theta here. And so that works out to the integral of 50 pi times sine, which gives me minus cosine pi over 4 plus 1, which is this. So there's the surface area. So I cannot emphasize to you enough how important it is to calculate the speed and calculate it carefully, right? If you mess up the speed, everything else is wrong, right? So it's so important to calculate the speed as carefully as you can. This one's kind of like, yay! After this, it's like, hey, this is worth 5 points and this is also worth 5 points. I know, but life isn't fair, you know? But sometimes you find $20 laying on the sidewalk, right? This is kind of that. So, I'm sorry if I'm saying things and you still got this wrong. So multiply this by r. You get r sine theta, 3r cosine theta plus 6. That is y. That is x. That is 6. We all agree. So y equals 3x plus 6. That's Cartesian because it's got x and y in it and nothing else. Es bueno? Okay. Those of you who didn't get this problem, in your heart you know you should have. And you also know that you will get it on the test if I asked something similar, right? These are not bad. This one requires a little bit more tinkering. So again, a nice method for this kind of problem is the reason I provide 2 graphs is basically just so that you can first make the graph of r versus theta. That just guides my thinking. So I go 0 over to 2 pi. And as you go from 0 to 2 pi, it's only going to 0 at 3 pi over 2. And it's got radius 1 here, here, and here. It's got radius 2 out here. And so that's what I draw. We start at radius 1, go out to radius 2 at pi over 2, go back to radius 1, and then this part right here gives us this. It drops to 0, and then it comes back out like that. And you can also see by this that there's kind of a symmetry of the side, so it should look somewhat symmetrical, something like that. So this is, I think this is a cardioid, right? And so to calculate the area enclosed by the curve, we just integrate from 0 to 2 pi, right? It's pretty, there's nothing too sneaky there. I guess it is sneaky. Well, what could be sneaky is if it happened to be the case that there are different curves which would suggest different ranges of integration, okay? That's all I'm saying. Right? So there's some thinking required to come up with the 0 to 2 pi. But then this is 1/2 the radius squared. There is no inner radius, right? So we just integrate the radius squared with respect to the theta divided by 2 as we derived. So sine theta integrates to 0 from 0 to 2 pi. 1 and the sine squared. So like the d theta integrates to 2 pi, we all agree. I showed you guys this trick another day. If I'm integrating sine squared theta from 0 to 2 pi, well, since sine squared theta and cosine squared theta are basically the same, take on the same values, it stands to reason that the integral of sine squared theta should be equal to the integral of cosine squared theta. So 2 times the integral of sine squared theta should be the integral of sine squared plus cosine squared, which is 2 pi. Anyway, long story short, that's pi. So that's something just worth knowing. I showed you guys how to think through that in terms of symmetry another day. Should I go back through that again? I mean, you can do this with a double angle formula too if you want, right? I just get bored of integrating sine squared, so I didn't write down steps, guys. Here are the less clever steps. Because the sine term gives us sine of 4 pi or sine of 0, both of which are 0. So anyway, it's good. Interrupt me at any point if you've got a question. I can't help but wonder if you can actually do this integral. I haven't tried yet, but I have a suspicion you might be able to. Here's the integral that gives you the arc length of the cardioid. So I just got to calculate dx d theta, dy d theta. It's not particularly pleasant, but they are kind of symmetrical, you know? I got like a cosine squared minus sine theta. Over here I got like a cosine theta plus 2 sine cosine. And I feel like if I square these out, there's going to be some like sine squared plus cosine squared happening. And there's other various things. This might simplify. It might actually be possible to do this integral. I'm not sure, but. Any questions? Your formula might look very different because you might have differentiated this in like a different looking way, and that wouldn't make it wrong. If the grader counts it wrong, please let me know about it. But he shouldn't count it wrong. It's possible to have your answer look quite different than mine. I will try to communicate this to the grader so that you guys don't lose points here. I'll do my best to communicate that. Okay? This one's more fun. Area outside r equals to 1 and inside r equals to 2 cosine 2 theta. Again, I make a graph of the r equals 1 I don't need to think about. I know what that is. That's a circle. Okay. This one I have to think about. So r equals 2 cosine theta, and the r theta is like this. And that gives me, like, this is one petal, then another petal. Here, let me do it over here. So like from pi over 4 to minus pi over 4 is like that, right? And then I hit negative r in the next part of the graph, so then I go down here like this. And then I'm to 3 pi over 4, and then to 5 pi over 4, and then I loop back up here from going from 5 pi over 4 to 7 pi over 4, where it's negative, so it gets flipped, right? So anyway, it's a flower with 4 petals. And so the area that's outside 1 and inside r equals 2 cosine theta would be these 4 pieces. So of course you could quadruple the area from, say, theta naught to minus theta naught to theta naught. But after I wrote that, it dawned on me, oh, why don't I just, like, what's the word for 8 times something? I don't know. Whatever that is, do that. From 0 to theta naught, right? By the symmetry of the problem. So I do that in the next step, and I figured out that the theta naught, the point of intersection here was at pi over 6. How I got that was that that's where 2 cosine 2 theta naught has to be equal to 1, right? So that means that 2 cosine 2 theta naught is equal to a half. How can I get cosine of theta equal to half? That means that I'm putting in pi over 3 into the theta function, the cosine function rather. So 2 theta naught is pi over 3, which gives me theta naught is pi over 6. You could use a calculator if you want, whatever. And so I'm faced with this integral, which is standard. I will post this solution in Blackboard when I get a chance. So, S bueno. I mean, it's good. It's no good. I'd never want to play poker with you guys. Let's see here. I mean, I don't know the rules of poker, so that's part of the problem. But and I didn't write the solution out to this here, but I have a solution written out to it somewhere else. Let me find it. I can't remember which one it was. Ah, there we go. I was recycling, as you can see. All right, here we go. Ninja Bob takes 2 whole minutes to prepare an attack, and his path is given by x1 equal to 16 thirds minus 8t over 3, and y1 equals 4t minus 5. On the other hand, the turtle known as Sky, of course, follows a path x2 equals 2 sine pi t over 2, and y2 equals minus 3 cosine pi t over 2. Both paths are described for t greater than or equal to 0 in minutes. Does Bob destroy the turtle Sky, or does the turtle get Bob before he's ready to counterattack? Find points of collision and intersection to answer this silly question. All right, so how did I do it? Oh, I found the Cartesian equation for Bob, and I found the Cartesian equation for the turtle, and then I looked for where they're both true. And after doing the algebra there, it revealed to me that x is equal to 0 or 2 at points of intersection. So then what I do with those, that gives me the points of intersection 0, 3, and 2, 0, plugging the x back into these to find the y, Like once I know x is equal to 0, y is equal to 6 over 2, which is 3. Once I know that x is equal to 2, then y is equal to 0 because 6 minus 6 is 0. And once I know that, then I can figure out the parameter times that it reached those points by just going back and solving 0, 3. That would give me 16 thirds minus 8t over 3 equal to 0, or 4 times 2 minus 5 equal to 3. So t equals to 2 for Bob at this point. But for the turtle, if I set this equal to 0 and that equal to 0, I also get t equals to 2. So it looks like the turtle and Bob meet at time 2. So time 2 is a collision point. And the collision point is 0, 3. However, the point 2, 0 is reached by Bob when this is equal to 0, which is 1.25 minutes. And 2, 0 is reached by Sky when t equals to 1 minute. Thus, Sky reaches 2, 0 before Bob and hence cannot hurt him. Ninja Bob wins.
Isn't that the opposite of the way the problem works? If Sky reached first, let Sky win. Because Bob's not ready yet. He hasn't turn and attack.
Oh no, my conclusion's wrong then, huh?
Yeah.
Oh. Well, this is very embarrassing. I should not be any kind of commanding our ninja. I have. Anyway, so the math here is pretty good. The conclusion, yeah, not so much. Sorry about that. I will try to fix it when I post for you guys. Okay. But yeah, I'll post. I mean, I can post this solution as is. It might take me longer to fix it, but I can post everything I just showed you momentarily. Let's see here. So I try to end class for you guys in here when, like about 15, 20 minutes from now, right? So what I was going to do in my classes. So let's see, when's our test? Tuesday. So we still got tomorrow to talk about homework and whatever. And we got Monday, right? So we got plenty of time for more examples. You get stuck on something as you're working out problems for yourself, you come get me. And bring it to a class and we can talk about it. But I thought I'd take the rest of today to do some. So I got. Yeah, this is nothing to do with course evaluations whatsoever, of course, yes. But I think I'm going to start a tradition in my classes, which is to bring. Let's see here. To bring. I know some of you are waiting to see this. Yeah, you guys are. I think I probably. And then of course you have to. So I thought I should bring some cookies, and part of that's because I'm going to ask you to fill out my own course evaluation, which I have drafted. And now I need one of you to collect these when you're done, and take them to the math secretary. She will hold them and not let me look at them until after your grades have been assigned, all right? So I promise I will not look at them until I assign grades. But it's basically just the usual questions, except I've added some commentary. I'm proud of some of my commentary, let me tell you. For example, well, first of all, there's room on here, so you can write as much as you want. If you got something to tell me about the class, tell me about it. But I also have included some important qualifiers. For example, number 17. The course integrated the subject with biblical principles. Here's what I have to say about that. Notice that all truth is God's truth. To answer negatively here would be to say that math is not part of God's truth. Do you really want to say that?
I'm just thinking about our discussion.
Just think about that. And then I have another one. The amount of time required in this course, e.g. studying, homework, assignment readings, and labs is reasonable. Here's my comment. This is not asking if the time was comparable to other courses you are currently taking. That which is worth doing is often difficult. What you should ask yourself here is, could I have done less and still understood the content of this course? Did I give you busy work, or did I give you work which you needed to build the skill which this course intends to impart to you? So anyway, I have concluded some commentary about these questions, because I think some of these questions are not helpful to you as students, actually, and they give you wrong ideas, and they poison your mind, honestly. Gotta be serious for a second here. And then at the last page, I have added a couple things like, number one, which topic should be added or removed from this course and why? And I'm going to reformat. This is what it is, but a student just suggested to me, I really should ask, what topics did you like the way they were presented in here? Which ones do you think need to be expanded on? That would be more useful to me. And then number two, is there a connection with math, engineering, science, etc.? Oh, misspelling. Which could be made to add breadth or interest. And so I asked that. What do you like most about this course? How the course be improved? Of course, the usual things. But you can say actually more than 50 characters here. You can write in the back, whatever. And again, I won't look at them until after. So what you could do is you come up here and get your course evaluation, grab some cookies if you want them. I'm going to pour some milk, and then I'll get out of here. So I figured this is, and you can, yeah, you can hit the camera.